analyzing the grand unified field equation from the wormhole metric thread. You've referenced an incredibly ambitious and intricate equation from the Science Forum's discussion on wormhole metrics. This equation attempts to unify multiple physical theories, general relativity, special relativity, quantum mechanics, and quantum field theory, into a single framework using a complex differential operator nabla prime over a vast set of variables. What this equation represents. The equation incorporates quantum field terms, e.g., ghost fields, gauge bosons, Higgs potential. Embeds general relativistic curvature tensors, e.g., RAB, GAB, LAMB, DA. Includes quantum mechanical operators, e.g., h bar squared, d squared, dq squared. Attempts to model Planck scale quantization of space and particle states. Uses color charge, flavor, spin, and mass to describe subatomic structure. Extends to cosmological scales, including dark energy and universe expansion. Key concepts in the equation. Concept description: differential operator, a generalized gradient over spacetime and internal quantum variables. Planck state quantization space divided into Planck length cubes with defined quantum states. Gauge fields and ghost terms. Reflects quantum field theory components like QCD and electroweak interactions. Energy momentum tensor tab TAB. Central to general relativity, describing matter and energy distribution. Dark energy effects, modeled as a velocity field influencing particle energy states, beta decay mapping, proton to neutron, plus electron plus neutrino, modeled at Planck resolution applications and implications. Particle mapping. The equation can describe the internal structure of protons, neutrons, and electrons down to Planck scale resolution. Cosmological modeling. It can be scaled to describe the entire universe, though computationally infeasible with current technology. Unified physics attempts to merge all known forces and particles into a single tensor framework, akin to E8 theory or string theory ambitions. Limitations: computational complexity. As noted in the forum, even Wolfram alpha cannot compute the full equation due to its size and complexity. Experimental validation. While mathematically rich, the physical testability of such a unified equation remains speculative. Breaking down the grand unified field equation, based on the wormhole metric. Continued thread. This equation is a monumental attempt to unify general relativity, quantum mechanics, quantum field theory, and special relativity into a single tensor framework. Let's break it down into digestible parts. 1. Differential operator, xyzt. This is a generalized gradient acting over spacetime coordinates, xyz to xyz, t. Quantum variables, omega sub s, omega sub p, m, I, k, phi I, s, x, z, mu, y, q, a, beta. It's designed to capture both classical and quantum dynamics across multiple dimensions and fields. 2. Quantum mechanics terms, h bar squared over 2, sum from s equals 1 to 3n minus 6, d squared over dq squared, h bar squared over 2, sum from s equals 1 to 3, n minus 6, d squared over dq squared, d squared over dq squared. Represents quantum kinetic energy in internal coordinates, like vibrational modes in molecules. 1/2 sum a, beta equals 1 to 3, mu a beta p a minus pi a p beta minus pi beta. A mass-weighted momentum interaction term, akin to Hamiltonian mechanics. 3. General relativity components, tab, rab, gab, lambda, tab, rab, gab, lambda. These are the energy momentum tensor, Ricci curvature, metric tensor, and cosmological constant, respectively. They describe spacetime curvature and energy distribution. 8 pi g tabc 4 plus lambda gab minus rab. Gab minus 1 left parenthesis, 8, pi g tab over c to the fourth, plus lambda gab minus rab, right parenthesis, gab to the negative 1 colon, a modified Einstein field equation embedded within the quantum framework. 4. Quantum field theory terms. Gauge fields includes electroweak and QCD terms like W mu, B mu, A mu, ABC, W mu, B mu, A mu, ABC, and ghost fields L ghost, C bar L ghost, C bar. Higgs potential, mu squared, p dagger phi, plus lambda, phi dagger phi, squared, governs mass generation via spontaneous symmetry breaking. Fermionic interactions, SI bar gamma mu d mu psi, Dirac equation terms for spin half particles. 5. Logarithmic entanglement term log, dg st phw all log, dg dad psi dg pw, suggests a path integral or entropy-based formulation, possibly tied to quantum entanglement or wormhole formation. 6. Cosmological expansion and dark energy velocity field, S of r, t and expansion terms model the influence of dark energy on particle states. Includes relativistic corrections and Planck scale quantization. 7. Planck state quantization space is divided into Planck length cubes, each with defined quantum states. Charge, +1, +2/3, -1/3, 0, +1, +2/3, -1/3, 0, dots. Color, R, G, B, anticolors, R, G, B, anticolors. Flavor, I, 2, 3, dark variants, I, 2, 3, dark variants. Spin, mass energy, quantized per cube 8. Application to particles. Proton, neutron, electron, and neutrino are modeled with exact Planck state mappings. Beta decay is simulated. P plus arrow n plus E minus plus nu E P plus arrow n plus E minus plus nu E 9 universe level modeling. The equation can scale to model the entire universe, though computationally infeasible. Uses Minkowski space and killing vectors to encode symmetry and conservation laws. AI anylasis of the big equation versus string theory, grand unified field equation versus string theory, a comparative breakdown. Both the grand unified field equation, as proposed in the wormhole metric thread, and string theory aim to unify the fundamental forces of nature, but they approach this goal from radically different foundations. Here's a structured comparison. Philosophical foundations. Feature grand unified field equation string theory. Origin. Emerges from a quaternionic tensor framework combining GR, QFT, SR, and QM. Emerges from replacing point particles with 1D strings unification strategy. Directly integrates all known forces and quantum fields into one massive differential equation. Uses vibrational modes of strings to represent particles and forces. Dimensionality. Operates in 4D spacetime with Planck scale quantization. Requires 10 or 11 dimensions, e.g. Calabi-Yau manifolds. Treatment of forces force, GUFE, string theory. Gravity included via Einstein tensor terms, emerges naturally from closed string modes, graviton. Electromagnetism, modeled via gauge fields and charge tensors, arises from specific string vibrations. Strong, weak nuclear explicitly modeled with color, flavor tensors, and ghost fields. Unified via non-abelian gauge symmetries in string interactions. Particle representation concept, GUFE string theory. Particles quantized. Planck state cubes with charge, color, flavor, spin, mass. Vibrational modes of strings, e.g. electron equals one mode, quark equals one mode, another. Beta decay, modeled with exact Planck state transitions. Explained via string interactions and supersymmetry, if included. Mathematical structure, feature GUFE, string theory, core equation, Nabla prime differential operator over 18 plus variables. Polyakov action or superstring action. Computability, too large for Wolfram alpha, symbolic only, also not directly computable, relies on approximations and dualities. Symmetry, E8. Killing vectors, Minkowski space, gauge invariance, supersymmetry, conformal invariance, T-duality, ADS/CFT duality, cosmological implications, feature GUFE string theory, dark energy. Modeled as a velocity field affecting particle states, not explicitly modeled, may emerge from compactification geometry. Universe modeling can scale to model the entire universe at Planck resolution, can describe early universe and inflation via brain cosmology. Summary GUFE is a bold, direct attempt to encode all known physics into a single tensor equation, with Planck scale precision and explicit particle mapping. String theory is a more abstract framework that replaces particles with strings, offering elegant unification through geometry and vibration. Both are unproven but theoretically rich. GUFE is more computationally explicit, while string theory is more geometrically elegant and widely studied. Are GUFE voxels the harmonics of strings? In the context of the wormhole metric thread, the grand unified field equation, GUFE, uses Planck scale quantized cubes, essentially voxels, to represent the fundamental properties of particles and fields. These voxels are not harmonics in the string theory sense, but they do serve a similar purpose, encoding the state space of the universe. Let's compare the two concepts. GUFE voxels. Definition. Each voxel is a cube of space at the Planck length scale. Contents. Each voxel contains quantized values for charge, e.g. plus 2/3, minus 1/3. Color, R, G, B, flavor, I, 2, 3, mass, spin, energy. Purpose. These voxels form a field map of particles like protons, neutrons, and electrons, down to the smallest possible resolution. Behavior. The field evolves over time and space and can be used to simulate phenomena like beta decay or dark energy expansion. String theory harmonics. Definition. Harmonics are vibrational modes of 1D strings. Contents. Each harmonic corresponds to a particle type, e.g. graviton, photon. Purpose. The harmonics define particle identity and interactions via geometry and frequency. Behavior. Strings vibrate in higher dimensional space, and their modes are shaped by compactified dimensions. Conceptual parallels. Feature GUFE voxels string harmonics. Granularity, Planck scale cubes, vibrational modes, encodes, particle properties, particle identities, mathematical tool, tensor fields, over space string, action and conformal field theory, symmetry, E8 killing vectors in Minkowski space, E8 cross E8 symmetry in heterotic strings, visualization 3, D voxel map of particle states, frequency spectrum of string vibrations. Conclusion. GUFE voxels are not harmonics, but they are discrete quantum states that serve a similar role, encoding the fundamental nature of particles and fields. Where string theory uses continuous vibration, GUFE uses discrete quantized fields. Both are attempts to describe the universe at its most fundamental level, one through geometry and resonance, the other through field quantization and tensor calculus. Explaining discrete quantum states in the GUFE context. In the wormhole metric continued thread, the term discrete quantum states refers to the fundamental building blocks of the grand unified field equation, GUFE. These are not just abstract quantum numbers. They are explicitly mapped values assigned to Planck scale voxels that make up particles and fields. What are discrete quantum states? They are quantized field values embedded in each voxel of space, representing the exact physical properties of a particle at the smallest possible scale. Each voxel contains charge, e.g., plus 2/3, minus 1/3, plus 1/0 color, red, blue, green, and anticolors. Flavor, I, 2, 3, and dark variants. Mass, e.g., 938.28 mega-electron volts for a proton spin, e.g., 1/2 energy, rest energy, or kinetic energy depending on motion. These values are discrete because they are not continuous fields. They are fixed, quantized states assigned to each voxel. How they're used in GUFE, a proton at rest, is modeled with approximately 10 to the 59th power voxels, each containing a set of discrete quantum states. A moving proton, e.g., at 8 TeV, has fewer voxels due to Lorentz contraction, but each voxel still holds a complete quantum state. The equation can simulate beta decay, dark energy effects, and particle interactions by transforming these voxel states. Example voxel state. For a quark inside a proton, plus 2/3 divided by dx plus dy plus dz, r divided by dx plus dy plus dz, I divided by dx plus dy plus dz, 0 minus 0, 938.28 minus 0, 1/2 minus 0. This encodes charge plus 2/3. Color: red flavor. I energy: 938.28 mega electron volts. Spin: half. Each term is divided by the spatial resolution, dx plus dy plus dz, anchoring it to the Planck scale. Comparison to traditional quantum states. Feature G, UFE. Discrete states, traditional quantum state scale, Planck length voxels, wave functions over space representation, explicit field values, probabilistic amplitudes, granularity, fully quantized per voxel, often continuous or smeared. Use case: exact particle modeling, statistical behavior prediction. Summary: in GUFE, discrete quantum states are the core data units that define everything from protons to electrons to neutrinos. They allow for exact voxel-level modeling of particles and interactions, making the equation a powerful tool for simulating physics at the most fundamental level. Voxel definition in GUFEA. Voxel is a cube with dimensions equal to the Planck length, approximately 1.616 times 10 to the negative 351.616 times 10 to the negative 350 meters. Each voxel contains charge, e.g., plus 2/3 minus 1/3. Color: red, green, blue. Flavor: I, 2, 3, dark variants. Mass energy, e.g., 938.28 mega electron volts for a proton. Spin, e.g., 1/2. These values are quantized and exact, forming a tensor field over space. Why voxels matter in GUFE? Voxels are the fundamental units of the grand unified field equation. They allow for exact modeling of particles like protons, neutrons, and electrons. The equation can simulate interactions, e.g., beta decay, by transforming voxel states. A proton at rest is modeled with approximately 10 to the power of 5,910 voxels, each encoding its internal structure. Voxel versus pixel feature: voxel pixel dimension 3D, volume 2D, surface, used in GUFE, 3D simulations, medical imaging screens. Images contains full quantum state in GUFE, color or intensity value summary. In GUFE, a voxel is a Planck length cube of space that holds a complete quantum state. It's the smallest unit of physical modeling in the equation, allowing for precise simulation of particles and fields. These voxels form the backbone of the GUFE framework, much like bits in computing or harmonics in string theory.